Okay, so this is going to be pretty quick, but I put this part 2 in here because I wanted to make sure that you were clear when you looked at molecules that you weren't confused by these different wedges and dashes. And this all goes back to the VSEPR theory, if you remember that from first semester chemistry, which details the three-dimensional structure of molecular geometry. So how about this? You're riding on a bus, and other than you, the bus is empty, and somebody else comes on the bus, and they come up and want to sit right next to you. Why, oh, why would they do that? Because there's the whole rest of the bus for them to sit. Why would they crowd you like that? Or guys, has this ever happened to you? Haha, you got this whole line here and somebody comes up and stands right next to you. That's really awkward, right? Well, the electrons and the bonds coming off an atom are the same way. They don't want to be crowded. Nobody wants to be crowded. So everything tries to stay as far apart as possible. So the hydrogens, if you have a carbon here, the hydrogens coming off of the carbon to make the four bonds are going to try to stay as far apart as possible from each other, right? When something is too crowded, it has too much in one area, like let's say this has this right here, and then the hydrogen comes off right here. Let's say if this were to happen, well, that's all crowded up there. Why? Okay, that's called steric hindrance, when it's too crowded for anything else to fit. So what ends up happening is, even though the way I drew it was I did hydrogen, like this is carbon, hydrogen, 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 to try to get them to stay as far apart as possible, right? But when you draw it like this is flat on a flat piece of paper or on the flat screen. So I just have them, 90 degrees away from each other like this, right? So this is 90 degrees, this is 90 degrees away from each other. But reality is in 3D, not 2D, not two dimensions on a piece of paper. It's in 3D. So really, that's incorrect. What is going on is that you have this carbon and it'll have, you know, two bonds coming off down here like this, and then it'll have one coming out of the center here and sticking out coming towards you. And then you'll have one around back, and I'll just make this little teeny tiny thing here, like you can see it, just so you can see what I'm talking about. This one's coming off of the back. So when you actually measure how far apart these end up being 120 degrees apart from each other. See, they're much further apart than the 90-degree one, where I just drew it like a clock, like noon, 3, 6, and 9, the hydrogen's coming out. So that's not what happens. They, just like this little guy right here, he's got his legs apart from each other, but then he's twisted, and so now his face and his upper body's facing this direction, and so his arms are coming out on either side of him, just like the feet are, but it's perpendicular to how the feet are spread apart. So that's the same thing here. It's going to be one's coming out the front, one's coming out the back, but that's really hard to draw. So the reason we can tell where the bonds and the electrons are situated on the atom is because of the steric number and molecular geometry. And remember, this is the VSEPR theory from first semester Gen Chem. But so see, this is going to be linear, and the A means like the central atom. That would be like the carbon, how I've been drawing. So it'd be a carbon, and then if it only had two bonds, one would come out there, one would come out there, because that's as far apart from each other as you can possibly get, right? That's 180 degrees. And so that would be in a straight line, and that would be called linear. But as soon as you have, and I'm going to stop, carbon has 4 bonds, so I'm going to actually just draw a generic atom there instead of carbon, because I don't want you to get confused, because carbon's going to always have 4 bonds. So that's just generic atom. We'll just go A for atom, just like in the formula here, A for atom. Now, if it has 3 things coming off of it, like here's the A for the central atom, and then it has 3 bonds. So here's a bond coming off of here, and the X is just for some generic bond. And so it's going to have one coming off of here and one coming off of here. So these can be as far apart as possible, right? And they're going to be evenly spaced too, if I didn't mention that already. And this is called trigonal planar. Trigonal, because tri means 3. So trigonal, it's going to have 3, like a triangle. Triangle, 3 sides, 3 points. So it's going to have 3 points to it. And planar means it's still going to be flat, because there's no possible way you can make this into 3 dimensions. It's just going to be flat no matter which way you turn it. Now, if you have 4 things coming off of it, then that's called tetrahedral, because tetra means 4. So tetrahedral, and it's going to have the central atom here, A for atom, and it'll have one coming off of here, one coming off of here, one coming out front, and then one going back, like out from behind the atom. You can't really see it, so we just draw it like this. And so that's tetrahedral. Now, when you have, like, here's the trigonal planar, right? So these are equally spaced apart from each other, right? But and that's 3 bonds. 1 bond, 2 bonds, 3 bonds, right? But if you have only 2 bonds coming off of it, 1 bond, 2 bonds, and the third thing, instead of this being another bond, it's a lone pair of electrons. Okay, that still counts. the lone pair of electrons still counts just like a bond. They want to stay as far apart away from each other as possible. So you're just going to replace one of the bonds with the lone pair. So it's still going to have that same shape, and it's still going to be the same amount of space in between each thing. But it's not necessarily bonds, it could be the lone pair. So each thing, whether it's a bond or a lone pair, each thing coming off of the central atom contributes to what we call the steric number. And remember I said steric hindrance is when everything's too crowded. So steric is referring to the things that are coming off of the central atom. On the left, we have 3 bonds coming off the central atom, but on the right, we have 2 bonds coming off the central atom, and where the third bond was, we instead have a lone pair. So in either one of these structures, the steric number is going to be 3 because there's 3 things coming off of it in 3 different directions. It doesn't matter if it's a bond or a lone pair, it still counts in the steric number. So what you want to do for the steric number is you want to just look and see all the different directions things are coming off of it. So if this is a bond or if this is a lone pair, it doesn't matter. It's just this, whatever this is coming off in this direction, whatever this is coming off in this direction, this is coming off in this direction. It could be a bond or it could be a lone pair. It doesn't matter. So 1, 2, 3 different directions, things are coming off of the central atom. That's why it's steric number 3. If it had 4 things coming off of it, then it would be, the steric number would be 4. If it had 3 bonds coming off of it and a lone pair, the steric number would still be 4 because there's 4 things, 4 different directions where things are coming off of the atom. So it doesn't matter if it's bonds or lone pairs, it's just how many different directions are things coming out of the atom is the steric number. So what do you do with that steric number? Well, let's say the steric number is n. So you want to just take whatever the steric number is minus 1. And that is going to be your SP number. This is called hybridization. The reason why you minus 1 is because there's always 1 for the S. S always gets just 1. We just don't write the 1 because, as you know, if it's just 1, it's just an invisible 1. It's just implied that that means 1 if there's no other number up there. And so that accounts for 1 out of the steric number. And then the rest of whatever your steric number is going to be on the P. So if you have a steric number of 3, like over here in the middle, this is steric number 3, this is steric number 3. You have 1 for the S, and then out of 3, and then you have 2 left over to make 3, right? So the 2 goes in the P. So whatever the steric number is, however many different directions things are coming off the atom, 1 less than that is what you put on the P. So you can have SP, which is this linear because you have 1, 2 things coming off of the central atom. So 2 minus 1 is 1, so P is going to have just 1 on it. This is 3. It's got 1, 2, 3 things coming off of the central atom. And this E means lone pair. 1, 2, 3. So 3 minus 1 is 2. So it's going to be SP2. And so if your steric number is 4, so 1, 2, 3, 4 things coming off of it, then 4 minus 1 is 3. So it'll be SP3. And that's it. No big deal. So now let's look at this in the line bond structure that I was talking about in part 1 of the video series. So here's one up here. Let's look at this top one. And let's look at this central carbon right here. Okay, so this carbon has an H, and then another bond to another carbon, and a bond to another carbon. So that's steric number 4. There's 4 things, right? 1, 2, 3, 4 things coming off of this carbon. So that's steric number 4. So N is 4. And the formula is sp n minus 1. So that would mean this is an sp3 hybridization. Let's look at this double bond here. Let's look at this carbon right here on this double bond. Well, it has this hydrogen coming out, that's 1, another bond to this carbon here, that's 2, but then it has just a double bond coming out to this other carbon. So that's only 3 because the double bond counts as one thing because that's going in the same direction, right? So that's going to be steric number 3, which means it's going to be sp2. Now let's look at this triple bond down here. Let's look at this carbon right here. The carbon's got a bond to another carbon on the left, and then it just has one more direction where things are coming out at that triple bond. So that's 1, 2. So that's steric number 2. So that means this is going to be sp1. So sp1, but we just don't write the 1. So how do you know when you're drawing, you have to draw things in 3 dimensions as opposed to 2 dimensions? Well, anything that's 2-dimensional, you don't have to worry about things going in the back or things going in the front or whatever because it's just laid out flat. Even in real life, it would just be flat. See, this is kind of like a frisbee shape, right? So it's a flat frisbee. This is kind of a frisbee shape. So SP and SP2 are just flat. They're planar. That's what planar means. But then as soon as you get into SP3, that's when it turns 3-dimensional. See, you have 1 direction, 2 directions, 3 directions, 4 directions. So the steric number is going to be 4. It's going to be SP3. Same for here. 1, 2 directions, 3 directions, 4 directions. Same thing. So the SP3 is the only time you have to worry about drawing it to represent the fact that it's in 3 dimensions. And if you haven't already, it's very helpful for a lot of people for an organic chemistry kit. And it's just like, like a kid's Lego set or something, or an erector set, and piece the different atoms together in real life. So you can actually hold it in your hand and see in 3 dimensions in real life what that atom looks like. So when we're actually drawing this, it's really hard to draw things to make it, to make it obvious this one's coming out toward you. This one's actually in back. You actually can't really see it because it's in the back, but you have to draw something to indicate it's back there. And then this bond's coming off the side. That's really hard and it takes too long, right? So how do we actually represent that on the page? Well, we do wedges and dashes. The wedges are the ones that are coming towards you, they're pointing at you, and the dashes are going away from you. And so here's how it looks. We have, when we're drawing this carbon right here, and we just have these bonds coming off of the sides, but the one, since this has 4 coming off of it, right? It's in 3 dimensions. So we draw a big wedge like this to represent it's coming toward you out of the page, toward you in 3 dimensions. And these dashes back here means it's back in the back and it's pointing away down into the page away from you. So here is another example of that where you can see it. See, this is just a flat bond, but then this means it's in the back and it's getting smaller going away from you, and this means it's in the front coming towards you. So really, when we're drawing these carbon skeletons, we just draw it like this. We just draw these like this, right? Because we don't put carbon on there because we always know that every corner is a carbon, right? And we don't normally draw the hydrogens on there. So it's just assumed that carbon always has 4 bonds. So whatever bonds we don't see, like here's 1 bond, here's 2 bonds. So there's 2 left. So we know there's going to be 2 hydrogens, right? But so really, since this is an sp3 hybridized atom, the carbon is, because it's got 1, 2, 3, 4 things coming off of it, really what we would do is we would draw one of these hydrogens with a wedge coming toward you and the other hydrogens with little dashes going away from you. And then the other 2 are just flat. So you just draw those with regular lines. So once again, just so you can see it. So we would have a hydrogen with a wedge and a hydrogen with dashes. So this is going away, and this is coming towards you. And so that is how you represent 3 dimensions of these molecules when you're drawing them on paper.